In this video, I'll share how to apply the exponential model to resource consumption, an important sustainability issue. In particular, I'll show you how to compute accumulations of a quantity using exponential models and explain the ideas of static and exponential reserve indices. Let's start with a version of a stock flow system that we considered earlier in the semester, a bank account balance. Suppose a bank account has $800 being deposited yearly with a 3% annual interest rate. How much money will be in the bank account after 5 yearly deposits? If we were to diagram this, we would have a single stock, the account balance, but two inflows, the deposits and the interest earned. This means that we have to coordinate the two inflows to describe how the stock changes over time. After the first deposit, the account balance is $800. 1 year later, after the second deposit, we add another $800, but we still have the previous $800 along with the interest that was earned on that $800. Note that I'm using the exponential growth model here to compute the interest. After the third deposit, we'll again have added another $800, and then we'll have added interest onto the previous balance. So here I'm taking the previous balance, and I'll multiply that by 1.03 to represent the new interest earned. I can rewrite this whole thing as 800 plus 800 times 1.03 plus 800 times 1.03 squared. Continuing this process, after the fifth deposit, I end up with 800 plus 800 times 1.03 plus 800 times 1.03 squared plus 800 times 1.03 to the fourth plus 800 times 1.03 to the fourth. This previous one should be third. Calculating this, we end up with 4,247.31. In other words, the account balance will be $4,247.31. We can generalize the previous calculation in the following way. Suppose the consumption or production of a quantity grows exponentially with initial quantity S0, a growth constant R, and a time step t. Then the total amount consumed or produced after n time steps is given by the sum you see on the left. This is the same calculation we did on the previous slide, where S0 is equal to 800, R is equal to 0.03, N is equal to 5, and T is equal to 1 year. On the right side, you see a shortened version of this calculation. Let's check our calculation from the previous slide using this formula. We would have 800 times 1.03 to the fifth minus 1 all over 0.03. This again comes out to be 4,247.31. This accumulation formula is useful for understanding the consumption of a finite resource, say a fossil fuel. The basic idea is to predict how long it will take to use up a resource, given certain patterns of consumption. Let's start by making our thought experiment more concrete. Suppose there is a reserve of size R, meaning this is the total quantity of that resource remaining, and that the resource is being used at a rate of Q units per year. If the rate of consumption remains constant in future years, then the reserve will last R over Q years. This is the static reserve index. Another possibility is that consumption grows exponentially, say with a growth constant R. We saw in earlier videos that this fits human patterns of consumption in many instances. To determine how long the reserve will last in this case, we can use our previous work to express the total consumption at any given time. I can compute this using the accumulation formula I shared earlier in this video. Then we are asking when total consumption is equal to the reserve, so I set these two quantities equal to each other. We're interested in the time it takes for total consumption to equal the reserve, so we're solving for n. Using algebra, including the log rules, I come up with the following formula, which gives the exponential reserve index. At the end of the video, I'll work through the derivation of this formula for those of you who are interested. But first, I want to apply these ideas to an example. Let's look at the example of coal in Britain. The Industrial Revolution of the 19th century was largely fueled by coal-powered steam engines. Britain had an abundance of coal, which allowed it to take a leading role in the new economy. But of course, coal is a finite resource. In 1865, the British economist William Jevons tried to calculate the reserve index for British coal. He estimated reserves at 10 to the 11th tons, meaning that R is equal to 10 to the 11th. And current consumption at 10 to the 8th tons. Now, note that if consumption was constant, we would look at the static reserve index, calculating R over Q, which comes out to be 10 to the 3rd, or 1,000. That is, if coal consumption remained flat, coal reserves would last 1,000 years. From a practical standpoint, this is almost an inexhaustible supply. But importantly, coal consumption in Britain was growing at about 3.5% per year. That is, R is equal to 0.035. Therefore, we can use the exponential reserve index formula to predict how long British coal would last. Look at N is equal to the log of 1.035 times 10 to the 11th over 10 to the 8th, all divided by the log of 1.035. This comes out to be 104. That is 104 years after William Jevons did his calculations. He estimated that British coal would run out. That's in 1979. Here's a graph of actual British coal production. You can see that the coal production does appear to grow exponentially for several decades before dropping in the early 1900s. Here, the exponential reserve index calculation doesn't perfectly predict the path of British coal production, but it does give us a reasonable understanding of the limits of this resource, and certainly better than the static reserve index would. For those of you interested, here's a derivation of the reserve index formula. Keep in mind that I'm solving for n, so I want to try and isolate that. My first step is to move the q and the r on the left-hand side over to the right-hand side. So I'd have 1 plus r to the n is equal to capital R times little r over q. Then I can take the log of both sides. So I would get the log of 1 plus r to the n is equal to the log of little r times big R over q. Keep in mind the second rule of logs. I can move that n out of the exponent out to the front. So I would get n times log of 1 plus r is equal to the log of r over q. Now I simply divide by the log of 1 plus r. So I get that n is equal to the log of r over q, all divided by the log of 1 plus r.